In this lecture, we will have a look at larger scales and explore the world of galaxies. Here is one of the most beautiful illustrations of the diversity of galaxies, the Hubble Ultra Deep Field that we already saw before. It reveals all sorts of galaxies up to faint, large magnitudes, so it shows very distant galaxies that emit little light. It is possible to see galaxies up to a magnitude of 29. The image consists of about 10,000 galaxies within an area of about 1/100th of the surface of the full moon. Each of those galaxies contain from about 100 million to 100 billions of stars. We live in one of some 80 billions of galaxies that populate the universe, the Milky Way. In this video, we will look at the various types of galaxies, how to study them, and how to understand their formation process. Let's see how galaxies are characterized through the Hubble sequence. This is a sequence proposed by the American astronomer Edwin Hubble at the beginning of the 20th century. The Hubble Space Telescope and the Hubble Law were named after the same astronomer. So Hubble established the evolutionary sequence, which in fact, as it will be shown later, is not evolutionary. This is just a morphological sequence describing the galaxies. There are essentially two types of galaxies, elliptical and spiral galaxies. In between, there is an intermediate type, the lenticular galaxies. What is going on in this sequence? The elliptical galaxies, as the name indicates, have an elliptical form, and they generally consist of old stars with random orbits around a common gravity center. E stands for elliptical. Then there are 7 possibilities for the ellipticity. The type of an elliptical galaxy can be written as E with an index n. That is equal to 1 minus a divided by b times 10, where a divided by b is the ratio of the semi-major axis and the semi-minor axis. The ellipticity 0 indicates a circular galaxy, while 7 includes the most elliptical galaxies. The spiral galaxies form large spiral arms. Those galaxies are seen face-on. Seen edge-on, they would show a disk component. Some examples will be shown in a moment. There are 2 groups of spiral galaxies. In general, S stands for spiral. Then the indices A, B, and C depend on the importance of the bulge compared to the spiral arms of the galaxy and the opening of the spiral structure. Going from A to C, there are less spiral arms, and they are less wrapped around each other. Spiral galaxies, as was said before, have a bulge that can be seen in the center. They also have a disk. It is in the flat disk, seen face-on here, that the spiral arms form. There is also a dark matter halo. The elliptical galaxies as well have a halo, which by definition cannot be seen as it is formed of dark matter. The halo will be discussed in the next videos. The lenticular galaxies were also mentioned. One can say that those are elliptical galaxies, but possessing a disk, through which one can even see dust. Those galaxies can be compared to the spiral galaxies, with a large bulge that has the size of an elliptical galaxy. As it was said before, the Hubble sequence is not evolutionary. Hubble created the sequence assuming that galaxies form as elliptical galaxies. Then they evolve progressively towards galaxies with spiral arms, either wrapped around each other or wrapped around a bar. Here we show barred spiral galaxies. They are formed using an S for spiral, B for barred, and then the index A, B, or C, which tells us how the spiral arms are wrapped around the bulge, and the bar in this case. Back to the evolutionary sequence, which is not evolutionary, as the elliptical galaxies do not evolve into spiral galaxies, as it was thought by Hubble. This is a mere morphological sequence. Be careful here. The Hubble sequence is a morphological sequence. Here are some examples of various types of galaxies, starting with an elliptical galaxy that is quite featureless, surrounded by a group of other galaxies. This particular galaxy lies at the center of a galaxy cluster in which the galaxies orbit, about a center of mass. Another example, this time a spiral galaxy, Messier 104. That is a magnificent example of a spiral galaxy SA with a prominent bulge that extends almost over the entire galaxy. A disk is seen inclined in the line of sight and is materialized by the line of dust across the galaxy. As it was shown in the previous videos, dust absorbs the background light. This is the reason why one can see the stellar light that is absorbed by the dust in the galactic disk. Another fascinating spiral galaxy, Messier 101, seen face on, with large spiral arms expanding from the center to the outer parts of the galaxy. One can clearly see the difference with the Messier 104. The bulge at this time is much smaller, as Messier 101 is an SB-type galaxy rather than SA. Finally, a barred spiral galaxy, NGC 1300. As its name indicates, it shows a bar that is placed in the plane of a galactic disk. Like the disks, bulges consist of stars, gas, and dust. Let's look in detail at the various types of galaxies. Starting with the elliptical galaxies, one could be seen here, in the center of a galaxy cluster. Quite often, elliptical galaxies lie in the center of a cluster, but not always. What is the mass range of the elliptical galaxies? Typically 10 and 7 solar masses for less massive, up to 10 and 13 solar masses for the most massive galaxies. The most massive elliptical galaxies often, but not always, lie in the center of a galaxy cluster. They consist of old stellar populations, i.e., of the age of about billions of years. There is little or no gas or dust. So the interstellar medium is quite poor. There is a little star formation. Stars are old with random orbits around the center of mass. Taking the cross-section of a galaxy in such a way, one can define the light profile. Y-axis represents the flux F, X-axis the radius of a galaxy. This is a typical light profile of an elliptical galaxy. Diepvall-Collier's profile, after the astronomer that defined this profile. The flux as a function of radius is equal to a normalization constant times expression R divided by RE and 1 divided by 4 minus 1. This is a typical light profile of elliptical galaxies. RE is the effective radius, i.e. the radius that contains half the total light of a galaxy. Let's take a look at the spiral galaxies. In spiral galaxies, there is a disk and extending spiral arms. Here we have an SAB galaxy, a type intermediate between A and B, the galaxy Messier 101, seen face on. The mass range is different for spiral galaxies. The least massive spiral galaxies are more massive than the least massive elliptical galaxies. However, the most massive spiral galaxies are less massive than the most massive elliptical galaxies, 10 and 12 solar masses instead of 10 and 13 solar masses, as it was for elliptical galaxies. The sizes are also valid for the elliptical galaxies, even if the elliptical galaxies are in general a little bit larger, i.e. about 40 kiloparsec in diameter. This limit is not quite precise, as around the bulge and the spiral arms there is a dark matter halo that is not visible, but the size of which can be estimated indirectly. In spiral galaxies, there is a lot of gas and dust, from which stars form. There are young stellar populations and a lot of star formation. In fact, there are two components of the stellar populations. The bulge consists of older, less massive stars. The reddish color implies that the peak in the black body distribution is in the red part. The spiral arms consist of young, more massive stars that radiate in the blue part of the spectrum. What is the light profile of spiral galaxies? Let's take the cross-section as before and look at the luminosity profile. Starting from the center, there would be two components. The disk component curve, so the flux as a function of radius, is an exponential curve. F equals FO E minus R divided by H, where H is the characteristic height of the disk. This is the luminosity profile of the galactic disk. On this curve, there will be superimposed the second component, the bulge. Its profile is obviously the de Van Coller's profile. The same that characterized elliptical galaxies. As it was seen before, this is another spiral galaxy, this time seen edge-on. If one takes a cross-section through the disk, with the flux on the y-axis and the radius on the x-axis, one will find a curve of the same type, an exponential curve with h as a characteristic height. Taking the cross-section at this point, the resulting curve will be the sum of the de Van Coller's profile that is characteristic for a bulge or an elliptical galaxy and a disk component. In this case, the measurements are affected by dust in the galactic plane. If our measurements are not affected by dust, the luminosity profile of a spiral galaxy, taken either perpendicularly or along the disk, would be an exponential function. What are the means that can be used to study those galaxies in details? There are two ways, through spectra or imaging. Starting with imaging, there is the bulge of a spiral galaxy, Messier 83 SAB galaxy. This bulge is characterized by the de Van Coller's luminosity profile. Then, there is also a disk component with a fraction of dust that is seen in absorption. This is a false color image, taken with three different filters. The first one is the H-alpha filter that shows gas, ionized by massive hot stars that are being formed. If one is interested in the zones of the star formation, one should look at the red areas whose spectrum can be presented on a diagram of the flux as a function of the wavelength. Typical spectrum of those areas is the black body spectrum with the peak in the blue part. As young, hot, massive stars emit most of the radiation in the blue. Then, here we would observe the H emission line. This image is taken using three filters, blue, intermediate color, and the H filter, that enables us to see these zones, that are the size of the sphere, which was presented in the lecture on the interstellar medium. It is interesting to take a closer look at the H emission of the gas ionized by young stars. Previously, in the lecture concerning the color magnitude diagram, it was shown that the stellar populations can be characterized by referring to the color magnitude diagram. This can be done in the different parts of the galaxy. For example, in this area with some young stars. Such a color magnitude diagram can be created using very high resolution images taken by the Hubble telescope. For example, one places the flux and color of all the stars from a chosen area on the color magnitude diagram. Then, the main sequence might be visible, maybe some other structure, but in any case, there is a possibility of characterizing the stellar populations that can be found in the marked area. Proceeding in the same way for different regions in the galaxy, it may be possible to trace back the history of galaxies' formation. In any case, the history of evolution of the stellar populations in the galaxy. All this thanks to some simple measurements of the flux and color of stars in various regions of the galaxy. If the image is taken at lower resolution and the stars cannot be resolved in those small areas, it is no more possible to use this method. In the previous image, a spiral galaxy, taken in three filters in the optical domain, was shown. Obviously, the observations can be made at much wider range of wavelengths. This is Messier 31. the Andromeda Galaxy in the ultraviolet, and in the infrared light. One can see the spiral arms and a part of the bulge, but it is more interesting to take a look at the spiral arms that are well marked by a great deal of bright points. In the ultraviolet, we can see hot mass of stars that ionize the surrounding gas, and so a lot of points can be seen in the H emission, as it was shown before. Looking at the far infrared image, there is some dust and gas concentrated in the galactic disk of the spiral galaxy. Dust absorbs photons coming from hot stars, and then emits a modified black-body spectrum, which peaks in the far infrared. One can easily notice that observing in the ultraviolet or infrared, the same galaxies can give information about various components. In the former case, one observes young hot massive stars in the process of formation. In the latter case, one can directly see the dust. Obviously, both images are alike as the stars heat the dust. Physically, both components are in the same place on the image. However, the physical processes that are observed are not the same. A multi-wavelength study of celestial bodies, in particular the galaxies, enable us to characterize the stellar populations, the gas contents, and to learn how those two elements are linked. Until now, we only studied the images, but there is also another important tool that can be used, the spectra. Those can be used to measure the Doppler effect. What can be seen here are the Doppler maps of some galaxies. Colors indicate a radial velocity of the stars as a function of the position in the galaxy. The red color indicates the velocity that is directed away from us. The blue color indicates the velocity directed towards us, idem for this galaxy. What can be measured is the velocity of the galaxy as a function of the radius, which in turn is used for the estimation of the galaxy's mass. This subject will be treated later. We can write the acceleration of the points along the rotation axis of a galaxy as a function of mass. We have g times m, r divided by r. That is, the gravitational acceleration is equal to v divided by r. This implies that v equals the square root of gm r divided by r. One can see that if the velocity at each point of the radius along the galaxy is measured, it is possible to calculate the mass within the radius. Once more, the Doppler effect turns out to be extremely useful. This time, it gives us the estimation of the mass of galaxies, the mass of luminous matter, as well as the mass of dark matter. We have discussed various diagnostics during this lecture: imaging, spectra, and a morphological classification. This morphological classification is not just to classify the objects. It is very useful to astrophysicists. The morphological classification changes with the distance. The distance is also the age of the universe. The universe was created during the Big Bang. It is expanding. Galaxies further away from us are closer to the Big Bang epoch. They are younger than the galaxies close to our own. If we established a morphological classification as a function of the distance, in the same time we established a morphological classification as a function of the age of the universe. Observing at various distances, we observe different epochs of the universe. Here we have a morphological classification giving the percentage of each type of galaxy in the local universe. 3% are elliptical galaxies. 15% are lenticular galaxies. 72% spiral galaxies. The majority are spiral galaxies. And 10% corresponding to galaxies that we are not able to classify. This is one of the observational facts. Another one tells us that if the same observations are obtained for galaxies further away, the results are not the same. Previously, there was 72% of the spiral galaxies. Now the spiral galaxies represent only 31%. The galaxies that are not classified represent 32% of the observed galaxies. These are the galaxies that are at a different evolutionary stage than in here. Those morphological classifications can be established as a function of distance regardless of theoretical tools at our disposal used to understand the observations. It is essential that those theoretical tools relate at the same time the morphological classification is a function of the distance. Masses determined using the measure of the Doppler effect and the rotational velocities of galaxies. They also have to relate to the study of the stellar populations that uses, for example, the color magnitude diagrams of the resolved stars from various regions in the galaxies, also as a function of the distance. Currently, the studies of the formation and evolution of galaxies make great progress from the theoretical as well as observational point of view. We have access to bigger and bigger telescopes that enable us to study galaxies which are further and further away. As the telescopes gather more and more light, it is possible to study galaxies with weaker and weaker intrinsic flux. And it is not all. In addition to large telescopes, there are smaller ones that specialize in detailed cartography of large fractions of the universe, maybe even the whole universe. It is possible to study large samples of galaxies, and with the obtained statistical properties from the observational point of view, and with progress in the data processing, and on the theoretical side as well, one can create simulations of entire chunks of universe containing billions of particles that are subject to gravitational forces, pressure, and even shock waves created by supernovae explosions in galaxies. It is now possible to confront theory and observations and to draw some conclusions about the validity of theoretical models.